Welcome to the Running Clearwater Reading Podcast. Today I will be reading Chapter 14 Semiconductor Electronics, Materials, Devices, and Simple Circuits. 14.1 Introduction. Devices in which a controlled flow of electron can be obtained are the basic building blocks for all the electronic circuits. Before the discovery of transistor in 1948, such devices were mostly vacuum tubes, also called valves, like the vacuum diode, which has two electrons, which anode, often called plate, and cathode triode, which has three electrodes, cathode plate and grid, tetrode and pentode, respectively, with four and five electrodes. In vacuum tube, the electrons are supplied by heated cathode, and the controlled flow of these electrons in vacuum is obtained by varying the voltage between its different electrodes. Vacuum is required in the inner electrode space, otherwise, the moving electrons may lose their energy on collision with the air molecules in their path. In these devices, the electrons can flow only from cathode to the anode, i.e., only in one direction. Therefore, such devices are generally referred to as valves. These vacuum tubes devices, like bulky, consume high power, operate generally at high voltages around 100 volts, and have limited life and low reliability. The seed of the development of modern solid state semiconductor electronic goes to 1930s, when it was realized that some solid state semiconductors and their junctions offer the possibility of controlling the number and direction of flow of charge carriers through them. Simple excitations like light heat or small applied voltage can change the number of mobile charges in semiconductor. Note that the supply and flow of charge carriers in the semiconductor devices are within the solid itself, while in their earlier vacuum tubes valves, the mobile electrons were obtained from a heated cathode and they were made to flow in a evacuated space or vacuum. No external heating or large evacuated space is required by semiconductor devices. They are small in size, consume low power, operate at low voltages, and have long life and high reliability. Even though cathode ray tubes CRT used in television and computer monitors, which work on the principle of vacuum tubes, are being replaced by liquid crystal display LCD monitors with supporting solid-state electronics much before the full implications of semiconductor devices was formally understood. A naturally occurring crystal of galena, lead sulfide, PBS, with a metal point contact attached to it was used as detector of radio waves. In the following sections, we will introduce the basic concept of semiconductor physics and discuss some semiconductor devices like junction diodes, a two-electron device, and bipolar junction transistor, a three-electrode device. A few circuits illustrating the applications will also be described. 14.2 classification of metals, conductors, and semiconductors. On the basis of conductivity, on the basis of relative values of electrical conductivity sigma or resistivity rho is equal to 1 by sigma, the solids are broadly classified as one metals. They possess very low resistivity or high conductivity, rho around 10 raised to power minus 2 to 10 raised to power minus 8 ohm meter, sigma varying from 10 raised to power 2 to 10 raised to power 8 siemens per meter. Semiconductors, they have high resistivity or conductivity intermediate to metals and insulators. Rho varying from 10 raised to power minus 5 to 10 raised to power 6 ohm meter. Sigma is its reciprocal. Insulators, they have high resistivity or low conductivity, rho varying from 10 raised to power 11 to 10 raised to power 19 ohm meter. The values of rho and sigma given above are indicative of magnitude and could well go outside the ranges as well. Relative values of resistivity are not only sub criteria for distinguishing metals, insulators, and semiconductors from each other. There are some other differences which will become clear as we go along in this chapter. Our interest in this chapter is in the study of semiconductors, which would be one elemental semiconductors, silicon and germanium, two compound semiconductors. Examples are inorganic semiconductors, which have CDS, GAAS, CDSE, INP, etc. Organic semiconductors, anthracene, doped with hyoscyamines, etc. Organic polymers, polypyrrole, polyaniline, and polythiophene, etc. Most of these currently available semiconductor devices are based on elemental semiconductor, silicon or germanium, and compound inorganic semiconductors. However, after 1990, a few semiconductor devices using organic semiconductor and semiconducting polymers have been developed, signaling the birth of futuristic technology of polymer electronics and molecular electronics. In this chapter, we will restrict ourselves to study of inorganic semiconductors, particularly elemental semiconductors, silicon and germanium. The general concept introduced here for discussing the elemental semiconductors by and large apply to most of the compound semiconductors as well. on the basis of energy bands. According to the Bohr atomic model, in an isolated atom, the energy of any of its electrons is decided by orbit in which it revolves. But when the atoms come together to form a solid, they are close to each other. So the outer orbits of electrons from neighboring atoms would come very close to or could even overlap. This would make the nature of electron motion in a solid very different from that in an isolated form. Inside the crystal, each electron has a unique position and no electron see exactly the same pattern of surrounding charges. Because of this, electron will have a different energy level. These different energy levels with continuous energy variation form which are called energy bands. The energy band which includes the energy levels of the valence electron is called the valence band. The energy band above the valence band is called the conduction band with no external energy. All the valence electrons will reside in the valence band. If the lowest level in the conduction band happens to be lower than the highest level of the valence band, the electrons from valence band can easily move into the conduction band. Normally, the conduction band is empty, but when it overlaps on the valence band, electrons can move freely into it. This is the case with metallic conductors. If there is some gap between conduction band and valence band, electrons in the valence band all remain bound and no free electrons are available in the conduction band. This makes the material an insulator. But some of the electrons from the valence band may gain external energy to cross the gap between conduction band and the valence band. Then these electrons will move into conduction band. At the same time, they will create a vacant energy level in the valence band where other valence electrons can move. Thus, the process creates a possibility of conduction due to electrons in conduction band as well as due to vacancies in the valence band. Let us consider what happens in the case of silicon or germanium crystal containing n atoms. For silicon, the outermost orbit is the third orbit, n is equal to 3, while for germanium, it is the fourth orbit, n is equal to 4. The number of electrons in the outermost orbit is 4, 2s and 2p electrons. Hence, the total number of outer electrons in the crystal is 4n. The maximum possible number of electrons in the outermost orbit is 8, 2s plus 6p electrons. So, for the 4n valence electrons, there are 8n available energy states. These 8n discrete energy levels can either form a continuous band or they may be grouped in different bands depending upon the distance between the atoms in crystal. At distance between atoms in the crystal lattices of silicon and germanium, the energy band of these 8n states is split in apart into which are separated by energy gap Eg. Figure 14.1. The lower band, which is completely occupied by the foreign valence electrons at a temperature of absolute zero, is the valence band. The other band, consisting of foreign energy states, called the conduction band. It is completely at absolutely zero. Figure 14.1. The energy band positions in a semiconductor at 0 Kelvin. The upper band, called the conduction band, consists of infinitely large number of closely shaped energy states. The lower band, called the valence band, consists of closely spaced, completely filled energy states. The lowest energy level in the conduction band is shown as E subscript C, and highest energy level in the valence band is shown as EV. Above EC and below EV, there are large number of closely spaced energy levels as shown in figure 14.1. The gap between the top of the valence band and bottom of conduction band is called energy band gap, energy gap EG. It may be large, small, or zero depending upon the material. These different situations are depicted in figure 14.2 and discussed below. Figure 14.2. Difference between energy bands of A metals, B insulators, and C semiconductors. Case 1. This refers to a situation as shown in figure 14.2a. One can have a metal either when conduction band is partially filled and valence band is partially empty, or when the conduction band and valence bands overlap. When there is overlap, electrons from valence band can easily move into conduction band. This situation makes large number of electrons available for electrical conduction. When the valence band is partially empty, electrons flow from its lower level can move to higher level, making conduction possible. Therefore, the resistance of such material is low or the conductivity is high. Case 2. In this case, as shown in figure 14.2b, a large band gap exists, Eg exists, Eg greater than 3 eV, 3 electron volts. There are no electrons in the conduction band and therefore no electrical conduction is possible. Note that the energy gap is so large that electrons cannot be excited from the valence band to conduction band by thermal excitation. This is the case of insulators. Case 3. This situation is shown in figure 14.2c. Here a finite but small band gap Eg less than 3 electron volt exists. Because of this small band gap at room temperature, some electrons from valence band can acquire enough energy to cross the energy gap and enter the conduction band. These electrons, though small in numbers, can move in the conduction band. Hence, the resistance of semiconductors is not as high as the insulators. In this section, we have made a broad classification of metals, conductors, and semiconductors. In this section, which allows you to learn the conduction processes in semiconductors. 14.3. Intrinsic semiconductor. We shall take the most common case of germanium and silicon, whose lattice structure is shown in figure 14.3. Figure 14.3. Three-dimensional diamond-like crystal structure for carbon, silicon, or germanium, with respective lattice spacing A equal to 3.56, 5.43, and 5.66 angstrom. These structures are called the diamond-like structures. Each atom is surrounded by four nearest neighbors. We know that silicon and germanium have four valence electrons. In its crystalline structure, every silicon or germanium tends to share one of its four valence electrons with each of its four nearest neighbor atoms, and also to take share of one electron from each of its such neighbor. These shared electron pairs are referred to as forming a covalent bond or simply a valence bond. These two shared electrons can be assumed to shuttle back and forth between associated atoms, holding them together strongly. Figure 14.4 schematically shows the two-dimensional representation of silicon or germanium structure shown in figure 14.3, which overemphasizes the covalent bond. It shows that idealized picture in which no bonds are broken, all bonds are intact. Such a situation arises at low temperatures. As the temperature increases, more thermal energy becomes available to these electrons, and some of these electrons may break away, becoming free electrons, contributing to conduction. The thermal energy effectively ionizes only a few atoms in the crystalline lattice and creates a vacancy in bond as shown in figure 14.5a. The neighborhood from which the free electrons with charge minus q has come out leaves a vacancy with an effective charge plus q. This vacancy with the effective positive electronic charge is called a hole. The hole behaves as an apparent free particle with effective positive charge. In intrinsic semiconductors, the number of free electrons Ne is equal to number of holes Nh. That is, Ne is equal to Nh is equal to Ni, where Ni is called intrinsic carrier concentration. Semiconductor possesses the unique property in which, apart from electrons, the holes also move. Suppose there is a hole at site 1 as shown in figure 14.5a. Figure 14.4 schematic two-dimensional representation of silicon or germanium structure showing covalent bonds at low temperature. All bonds intact. +4 symbol indicates inner cores of silicon or germanium. Figure 14.5a schematic model of generation of hole at site 1 and conduction of electron due to thermal energy at moderate temperatures. B. Simplified representation of possible thermal motion of a hole. The electron from the lower left-hand covalent bond site 2 goes to meet the earlier hole site 1, leaving a hole at its site, indicating apparent movement of the hole from site 1 to site 2. The movement of holes can be visualized as shown in figure 14.5b. An electron from covalent bond at site 2 may jump to vacant site 1 hole. Thus, after such a jump, the hole is at site 2 and the site 1 has now electron. Therefore, apparently the hole has moved from site 1 to site 2. Note that the electron originally set free, figure 14.5a, is not involved in this process of hole motion. The free electron moves completely independently as conduction electron and give rise to electron current, i.e., under an applied force field, applied electric field. Remember that the motion of hole is only a convenient way to describing the actual motion of bound electrons whenever there is empty bond anywhere in the crystal. Under the action of an electric field, these holes move towards negative potential, giving the hole current IH. The total current is I. Thus, the sum of electron current IE and the hole current IH. I is equal to IE plus IH. It may be noted that apart from processes of generation of conduction electrons and holes, a simultaneous process of recombination occurs in which the electrons recombine with holes. At equilibrium, the rate of generation is equal to the rate of recombination of charge carriers. The recombination occurs due to an electron colliding with a hole. An intrinsic semiconductor will behave like an insulator at T is equal to 0 Kelvin as shown in figure 14.6a. Figure 14.6a, an intrinsic semiconductor at T equal to 0 Kelvin behaves like an insulator. It is the thermal energy at the higher temperatures T greater than 0 Kelvin which excites some electrons from the valence band to the conduction band. These thermally excited electrons at T greater than 0 Kelvin partially occupy the conduction band. Therefore, the energy band diagram of intrinsic semiconductor will be as shown in figure 14.6b. Here some electrons are shown in the conduction band. These have come from the valence band, leaving equal number of holes there. Figure 14.6b, at T greater than 0 Kelvin, four thermally generated electron hole pairs. The filled circles represent electrons and empty circles represent holes. Figure 14.4, extrinsic semiconductor. The conductivity of an intrinsic semiconductor depends on its temperature, but at room temperature, its conductivity is very low. As such, no important electronic devices can be developed using these semiconductors. Hence, there is a necessary of improving their conductivity. This can be done by making use of impurities. When a small amount, say a few parts per million ppm of suitable impurity is added to pure semiconductor, the conductivity of semiconductor is increased manifold. Such materials are known as extrinsic semiconductors or impurity semiconductors. The deliberate addition of desirable impurity is called doping, and impurity atoms are called dopants. Such a materials is also called doped semiconductor. The dopant has to be such that it is not distort the original pure semiconductor lattice. It occupies only a very few of original semiconductor atom sites in the crystal. A necessary condition to attain this is that the sizes of dopant and semiconductor atoms should be nearly the same. There are two types of dopants used in doping the tetravalent silicon or germanium. One, pentavalent, valency 5, like arsenic As, antimony Sb, phosphorus T, etc. 3 trivalent valency 3 like indium iron boron B aluminum Al etc. We shall now discuss how the doping changes the number of charge carriers and hence the conductivity of semiconductors. Silicon or germanium belongs to the fourth group in the periodic table and therefore we can choose the dopant element from nearby fifth or third group, expecting and taking care that the size of the dopant atom is nearly the same as that of silicon or germanium. Interestingly, the pentavalent and trivalent dopants in silicon or germanium give two entirely different types of semiconductors as discussed below. One n-type semiconductor. Suppose we dope silicon or germanium with a pentavalent element as shown in figure 14.7. When an atom of plus 5 valency element occupies the position of an atom in the crystal lattices of silicon, four of its electron bond with the four silicon neighbors, while the fifth remains very weakly bound to the parent atom. This is because of the four electron participating in the bonding are as seen as part of the effective core of the atom by the fifth electron. As a result, the ionization energy required to set this electron free is very small, and even at room temperature, it will be free to move in the lattice of the semiconductor. For example, the energy required is about 0.01 electron volt for germanium and 0.05 electron volt for silicon. To separate this electron from its atom, this is in contrast to the energy required to jump the forbidden band, about 0.72 electron volt for germanium and about 1.1 electron volt for silicon at room temperature in intrinsic semiconductor. Thus, the pentavalent dopant is donating one extra electron for conducting, and hence it is known as donor impurity. The number of electrons made available for conduction by dopant atoms depends strongly upon the doping level and is independent of an increase in ambient nature. On the other hand, the number of free electrons with an equal number of holes generated by silicon atoms increases weakly with temperature. In a doped semiconductor, the total number of conduction electrons Ne is equal to the electrons contributed by donors and those generated intrinsically, while the total number of holes is only due to the holes from intrinsic source. But the rate of recombination of holes would be increased due to increase in the number of electrons. As a result, the number of holes would get reduced further. Thus, with the proper level of doping, the number of conduction electrons can be made much larger than the number of holes. Hence, in extrinsic semiconductor doped with pentavalent impurity, electrons become the majority charge carriers, and hold the minority carriers. Thus, semiconductors are therefore known as these semiconductors are known therefore as n-type semiconductors. For n-type semiconductors, we have number of electrons much greater than number of holes. Figure 14.7a pentavalent donor atom ASSBP, etc., doped for a tetravalent silicon or Si or Ge, giving N-type semiconductor, and B, commonly used schematic representation of N-type material which shows only the fixed cores of the substituent donors with one additional effective positive charge and its associated extra electron. 2. P-type semiconductor. This is obtained when silicon or germanium is doped with trivalent impurity like aluminum, boron, indium, etc. The dopant has one valence electron less than silicon or germanium, and therefore this atom can be forms covalent bond with the neighboring three Si atoms, but does not have any electron to offer to the fourth Si atom. So the bond with the fourth neighbor and the trivalent atom has a vacancy or a hole as showing in figure 14.8. Figure 14.8, a trivalent acceptor atom, indium, aluminum, boron, etc., doped in tetravalent silicon or germanium, that is giving a p-type semiconductor. Commonly used schematic representation of p-type material which shows only the fixed core of substituent acceptor with one effective additional negative charge and its associated hole. Since the neighboring silicon atom in the lattice wants an electron in place of a hole, an electron in the outer orbit of an atom in the neighborhood may jump to fill its vacancy, leaving a vacancy or hole in its own side. Thus, the hole is available for conduction. Note that the trivalent for an atom becomes effectively negatively charged when it shares a fourth electron with neighboring silicon atom. Therefore, the dopant atom of p-type materials can be treated as the core of negative charge, along with its associated hole as shown in figure 14.8b. It is obvious that one acceptor atom gives the hole. These holes are in addition to intrinsically generated holes, while the source of conduction electrons is only extrinsic generation. Thus, for such a material, the holes are majority carriers and electrons are minority carriers. Therefore, extrinsic semiconductors doped with trivalent impurity are called the p-type semiconductors. For p-type semiconductors, the recombination process will reduce the number Ni of intrinsically generated electrons to Ne. We have for p-type semiconductors number of holes much larger than number of electrons. Note that the crystal maintains an overall charge neutrality as the charge of additional charge carrier is equal and the opposite to that of ionized cores in lattice. In extrinsic semiconductors, because of abundance of majority current carriers, the minority carriers produced thermally have more chance of meeting majority carriers and thus getting destroyed. Hence, the dopant by adding a large number of current carriers of one type which become the majority carriers indirectly helps to reduce intrinsic concentration of minority carriers. The semiconductor's energy band structure is affected by doping. In the Case of extrinsic semiconductors, additional energy states due to donor impurities, ED, and acceptor impurities, EA, also exist. In the energy band diagram of N-type semiconductor, the donor energy level ED is slightly below the bottom EC of a conduction band, and the electron from this level move into conduction band with very small supply of energy. At room temperature, most of the donor atom of the gets ionized, but very few, about 10 raised to power 12 atoms of silicon gets ionized. So the conduction band will have most electrons coming from donor impurity, as shown in figure 14.9a. Similarly, for p-type semiconductor, the acceptor energy level EA will slightly above the top EV of the valence band, as shown in figure 14.9b. Figure 14.9, energy bands of A n-type semiconductor at T greater than 0 Kelvin, B p-type semiconductor at T greater than 0 Kelvin. With very small supply of energy on electrons from the valence band can jump to level EA and ionize the acceptor negatively. Alternatively, we can also say that with very small supply of energy, the hole from which EA sinks down into the valence band, the electrons rise up and holes fall down when they gain external energy. At room temperature, most of the acceptor atoms get ionized, leaving holes in valence band. Thus, at a room temperature, the density of holes in the valence band is predominantly due to impurity in extrinsic semiconductor. The electron and hole concentration in semiconductor in thermal equilibrium is given by NE is equal to Ni square. Though the above description is grossly approximate and hypothetical, it helps in understanding the difference between metals, insulators, and semiconductors, extrinsic and intrinsic, in a simple manner. The difference in the resistivity of carbon, silicon, and germanium depends upon the energy gap between the conduction and valence bands. For carbon, diamond, silicon, and germanium, the energy gaps are for 5.4 electron volt, 1.1 electron volt, and 0.7 electron volt, respectively. Tin also is a group 4 element, but it is a metal because the energy gap in its case is 0 electron volt. That's it for part 1. See you in part 2.